My name is Craig Gifford, and I'm a communications manager with SwageLock. Our webinar today is entitled Optimizing Gas Distribution, Accounting for Changeovers, Regulators, and More. Gas distribution systems are critical to the effective operation of many industrial facilities around the world. Despite the importance of these systems, however, opportunities to improve their performance and cost effectiveness are often missed or misunderstood. Increasing changeover pressure may seem like a good way to improve system flow, for example, but it often does so at the expense of bottled gas. Adding regulators may help you to control supply pressure, but it also adds cost to your system. So, how do you know what the ideal gas distribution setup is for you? Well, that's what we're here to find out today. Our talk today is being led by Joe Rodriguez, who's a senior applications engineer on SwageLock's custom order team. In this role, he is responsible for designing fit-for-purpose solutions for customer applications, managing projects from order receipt to delivery, and providing engineering analysis and support. He is the lead design engineer for the SwageLock gas distribution program, which involves working with a cross-functional team across the globe to develop flexible, pre-engineered gas delivery systems. In his 13 years with SwageLock, Joe has held roles in lab testing, new product design, and product engineering for tools and equipment. He has an application expertise involving grab sample systems, system flow analysis, automatic changeover assemblies, and oxygen system safety and design. Joe holds Bachelor of Science and Master of Science degrees in mechanical engineering from Cleveland State University. So as Joe is presenting today and you have questions, please feel free to drop them in the question button in your upper right-hand corner of your screen. And we'll cover as many questions as we can after Joe has finished his presentation. So with that, I will hand it off to you, Joe.
Craig, thank you very much. And thank you all for your time today. I do really appreciate it. Well, you've heard about the background, you've heard about what we're going to talk about, so let's dive right in. Here's a brief overview of the topics we're going to be going over today. We're going to begin with an exploration of regulator flow curves and some of the phenomena that we can pick up on those flow curves. Then we're going to talk about supply pressure effect in your regulators and how you can mitigate it using multiple regulation stages. And we're going to talk a little bit about changeover panels, how they work, how you may want to select your changeover pressures and line regulation. So looking at regulator flow curves, we see an example of a regulator flow curve on the right. This shows the outlet pressure of a regulator at a particular setting as the flow demand changes. There are three distinct sections to this that we want to talk about. The first, highlighted up top, is a bit of a steep drop on the far left. This is known as the lockup region. Once you get out of the lockup region, the next area of the flow curve represents the ideal operating range. And once you've gotten past the ideal operating range, you'll get to a steep drop in pressure on the far right, where choked flow occurs. In this state, the regulator is as open as it's going to get, and you have sonic choking occurring across the regulator's orifice. I'm going to focus a little bit more on seat load and lockup and then that ideal operating range here. In the lockup region, once again, the pressure will drop pretty sharply as you increase the flow demand from zero, but it'll level out pretty quickly as well. Generally speaking, you want to avoid operating your regulators in this region if you can. What should you do about it? Well, if you have a situation where you have a particularly pressure sensitive application, we do recommend that you set your regulators under some amount of flow to ensure that you have the full pressure that you need at your operating characteristics. Now, looking in the ideal operating range, the pressure drop still is present. It'll be a little bit more gradual as the flow increases, and this is a phenomenon we call droop. In this range, regulators are pretty predictable and fairly steady. Most cases, you don't really need to do anything about it. You've done well by selecting a regulator that is operating in this range for your application to begin with. However, if you do have a situation where you have wide flow demands, so in an example like you see here, if your flow demands range between, say, 40 and 100 SCFM, and you need to have very, very steady pressure controlled in that range, you may consider selecting a regulator that has an external pressure reference. By referencing the actual external downstream pressure in your system, the regulator has an opportunity to maintain that outlet pressure much more evenly across a wide variety of flow requirements. So the flow curve that we were looking at before was just a single flow curve, but it turns out that regulators actually behave a little bit more differently than that. The flow curves you can imagine as a set of flow curves or a family of them. On the right, we see two families of flow curves. On It's worth pointing out that this entire graph is a set of flow characteristics for a single regulator. The curves at the top represent that regulator when it's been set to a 250 psi static outlet pressure, and the curves at the bottom in gray are what you would expect if you set the same regulator to 100 psi. You'll note that with each set of curves, there's a number associated with it on the graph: 3600, 1000, and 500 psi. Those numbers are the inlet pressures on that regulator. So one of the things that I want to point out is that the change in the flow capacity, in other words, the reach in the horizontal direction of these flow curves, is very sensitive to that inlet pressure. As your inlet pressure goes down, your flow capacity also goes down. It's a lot less sensitive to your outlet pressure setting. You'll notice the top curves and the bottom curves share approximately the same sort of length and flatness. Why is this important? Well, very often in our gas systems, the very first thing in line is a bottle, a gas cylinder, some fixed volume that begins at a high pressure and will go through a drastic pressure change as you drain it. So as your cylinder drains, the pressure at the first stage regulator goes down. And as you can see on the flow curves on the right, your flow capacity will be reduced. Another reason that it's important to understand these families of flow curves is because very often in your gas distribution system, the flow characteristics will be governed by the last regulator in a series. And so the flow capacity of that regulator is going to be heavily dependent on its inlet pressure, which will essentially be the pressure setting of the regulator right before it. Now I'd like to talk to you a bit about supply pressure effect. Here we see an excerpt from the Swagelok K-Series regulator catalog, and it's just a brief little table in here that shows you what it is for various part number selections that you might make. But you'll notice it's got units of percent. Seems like an odd thing to do. What does it mean? Basically, your supply pressure effect says that the outlet pressure will change when the inlet pressure or supply pressure changes, and its direction will be opposite that of the change of the inlet pressure. So as the inlet pressure goes down, the outlet pressure will go up. And the ratio of those changes is the supply pressure effect in percent. It's a bit of a mouthful, and I'm more of a visual learner, so let's present a visual graph to help us understand this. I like to think of the supply pressure effect as a seesaw. In this case, we have an inlet on the right and we have an outlet on the left, and the length of the arm on the inlet is units of one. The length of the arm on the outlet would be our supply pressure effect in some percent. This could be 1%, for example, so it'd have a length of 0.1. And as we rock this seesaw up and down, that will be a representation of our pressures. So we remove our length brackets there and apply some pressure changes. You can see We're going to drop the inlet pressure by some large amount, and we're going to observe what happens to the outlet pressure. As you would expect, the outlet pressure moves in the opposite direction to the inlet, and with its magnitude being the supply pressure effect percent. So enough with the seesaws. What does this look like in an actual regulator? Well, let's take a Swagelok K series regulator. In this particular case, we've set it up with 3600 psi on its inlet. You can see the gauge on the lower left of your screen there on the inlet side. And we've set this up with a 50 psi outlet pressure. You can see the outlet gauge on the right. Now, the particular regulator that we've selected, we know has a supply pressure effect of 1%. We've looked it up in the catalog for this particular part number. And we're going to have a look at what happens as we decrease the inlet pressure. So you can see the yellow highlighted gauges are moving. Our inlet pressure is going down. Our outlet pressure is going up. Now let's stop the flow on this. We'll stop our inlet pressure from dropping at 2600 psi. So we've achieved a 1000 psi decrease on the inlet. So what does the outlet pressure look like? Well, we would take 1% of that 1000 psi change on the inlet, which is 10 psi. Once again, the sign changes. So because the inlet pressure went down, the outlet pressure will go up from 50 to 60 psi. So shown here is a Swagelok SGP panel with a single stage of regulation. This is exactly the sort of panel that would experience the phenomenon that we just looked at. Now, to get you a little bit of a sense of what you're looking at here on these panels, the inlet is at the bottom. You can see the inlet then feeds the single stage regulator with the green handle there. It has an inlet gauge poking out on the right. And the panel flow direction is up in this case, so the panel outlet is at the top. You can see an outlet gauge connected to the outlet of that regulator. We've got a relief valve on the left for safety. And we'll go ahead and highlight the regulator there as a reminder that this is in fact a single stage panel. Now, how does the supply and pressure effect affect our single stage panel here? Well, the relief valve setting is one thing that is often overlooked, and we have seen instances of this happening before. If your relief valve is located downstream, you need to consider how the supply pressure effect is going to work with it. It's very common to set the cracking pressure of a relief valve to something like 10% over your maximum working pressure. If you do that with this panel, and if the regulator is set at 100% working pressure, the supply pressure effect may cause the relief valve to open. In other words, your outlet pressure may exceed your pressure setting of the relief valve. Now, if this is the regulator panel that is correct for your application, and if you can afford to do so, you may consider increasing your relief valve pressure to something above your supply pressure effect accounted for in the outlet. But another thing that you may consider doing is trying to mitigate the supply pressure effect entirely. Once again, circling the relief valve just so you know what we're talking about here. So what strategies can we employ to mitigate the supply pressure effect? Well, one of the most common ways that we see is to have two regulators in series. So in this case, we're going to take two of the same regulator that we had before, and we're going to feed into the first regulator on the left a 3600 psi source. Now that first regulator, instead of being set to 50 psi on the outlet, we're going to set it to 500, and that'll be what we call the interstage pressure. That 500 psi then becomes the inlet to our second stage. Our second stage regulator has been set to drop that 500 psi inlet interstage pressure to 50 psi. So overall, the same inlet and the same outlet pressure of our system. We're going to go ahead and draw some flow through the system. And once again, we can see our pressure gauge is moving. Our inlet is dropping. Our interstage pressure is going up, as we would expect. Because the supply pressure effect works on both regulators, the outlet pressure of the second regulator goes down as the interstage pressure goes up. And we've stopped our flow. Once again, we've had the same 1000 psi decrease on the inlet. So let's see what happens to the interstage pressure. We have the same 1% supply pressure effect that we had before. So we have the same 10 psi increase. So our interstage pressure goes up from 500 to 510 psi. Going through the second stage of regulation, we take that 10 psi increase and we factor it through this 1% supply pressure effect again. And that results in a 0.1 psi decrease. So now our outlet pressure changes from 50 to 49.9 psi as a result of our 1000 psi inlet. So just to show what that would look like, here we have another Swagelok SGP panel. In this case, it's been specified very similarly, but with 2 stages of pressure regulation to help mitigate that supply pressure effect. Just as before, you're looking at the inlet on the bottom, and the outlet is on the top. The inlet and outlet gauges are similarly placed. The relief valve is similarly placed. So by and large, the same sort of panel. This time, the settable regulator with the green handle is the second stage regulator. And then the first stage regulator, which doesn't really need to change much, has an anti-tamper nut on it. So this is a non-adjustable regulator just to help mitigate the supply pressure effect. So once again, to directly compare these two examples, we have our single stage regulator at the top and our dual stage regulator panel on the bottom. And this time we've scaled the outlet pressure gauges a little bit more appropriately. So we can see once again, for the same change in the inlet, the outlet pressure has changed from increasing by 10 psi to decreasing by 0.1. So just by adding one extra regulator to the system, we've achieved a 99% decrease in the change of outlet pressure. Very, very drastic increase in performance. Now this will come with some trade-offs that we'll talk about in a little bit. Before we do that, I'd like to switch gears and start talking about changeover panels. So Swagelok actually offers 3 separate changeover panels: the KCM, which you can see on the right, the KCA, shown in the middle, and the SCO. This is our newest panel on the left. We're going to explore the SCO specifically for these examples, but the principles will apply to any of these regulator-driven automatic changeover panels. So first of all, what is a changeover panel? Well, at its most fundamental, it's either a 1 or 2 stage regulator panel, just like what we were looking at before. What does it do? Well, it has a bit of a twist. It takes 2 separate inlet sources, and it will only use one of those sources at a time until that source drops in pressure to some predetermined point. We call this the changeover pressure. And then it will automatically start drawing gas from the secondary source. This changeover action requires no intervention from the operator. It happens with no need to switch any handles or approach the panel at all, and it's all mechanically driven. So how does this work? Well, before we get into that, let's talk about why you might want to use one. Most often, it'll be when you have a process that absolutely cannot tolerate a supply interruption. We've had customers use these before for online analyzers. So say, for example, if they have a process gas chromatograph and they have hydrogen or some other carrier gas that needs to feed that, and they need a constant continuous flow. If they can't tolerate an interruption when they need to change a bottle, they will want to change over panel. We've also used them when there are critical purge gases needed. So a good common example is metal 3D printing. 3D printing has become very popular these days. When you do it with metal, you'll typically be sintering some metal powder at a very high temperature, and you need to keep oxygen away from that. So they'll be plumbing in some inert gas, argon, or some argon mixture. And if you don't want to have an interruption in your print, you may consider using a changeover panel for that. They're also useful if you want to extend uptime between your cylinder changes. So when one cylinder drops out, it will begin using the second cylinder, and you can get to it anytime between the use of that second cylinder. And that can be particularly handy if your gas is at a remote location that's not as easy to get to. So once again, we find ourselves asking, well, how does it work? It takes two inputs. Um, each of these inputs feeds its own dedicated regulator, and those two regulators have their outlets tied together, and that those outlets feed the outlet of the panel. One of those regulators will be set at a higher pressure than the other one, and the one that is set at the higher pressure will preferentially feed, so that will be the primary source. And then the changeover pressure, or the pressure at which it starts using the secondary source, will be the setting of the lower of those two regulators. So on the right, we see a little diagram of a very simple changeover panel. We see our two regulators, our two sources, and the single outlet. Let's apply some pressure to this panel and watch how it behaves. So here, all three gauges are in the same basic range. So we see source one and source two are both quite full. And due to the regulators, the pressure at the outlet has been dropped, in this case, about in half. And source one is the higher setting regulator, and we can see it's drawing gas from source one. And it'll do that until the pressure in source one drops to the pressure setting of source one. Now remember, source two will drive the changeover. It's set slightly lower. So once the inlet pressure of source one reaches the pressure regulator setting for source one, that regulator will be wide open, and it will continue to feed from that regulator until the outlet pressure drops to the setting of source two, at which point source two's regulator, which is sensing its downstream pressure, will say, hey, I see that the pressure is now approaching my set point. I need to start feeding gas downstream to keep that pressure up. So then this is where the changeover occurs, and the panel will begin drawing from source two, and will continue to do so until its source is depleted. So it's during that time that your panel is drawing from source two that you have time at that point to change out source one, which has been depleted. So, having talked about how they operate, let's talk a little bit about some of the important parts about selecting these. On the right, we see an excerpt from the Sway.Jock catalog for the SCO. And there are many things that you can choose in the part number, but we're going to focus on two things. The pressure control range. So if you have a line regulator on your SCO panel, you can choose the outlet pressure range of it. So you can go 0 to 100, 0 to 250, or 0 to 500 psi. But a lot of people are confused or perplexed by the none option. Well, if you have none selected for your pressure control range, you're asking for no line regulator at all. So that essentially means that you have the equivalent of a single stage regulator panel. When you have that single stage regulator panel, the supply pressure effect will apply, but the outlet pressure will vary by a little bit more than that. It will also vary by the difference in the regulator settings for your two changeover regulators. So commonly you'll expect that to be something in the range of about 60 psi, give or take. Now, if you do select one of the other options that includes a line regulator, that essentially makes this a two-stage panel. And as we discussed before, that's an effective strategy for limiting your supply pressure effect on the outlet. Now, when you consider the changeover pressure, First of all, the SCO is user selectable and you can pick it on any value between 50 and 500 psi. And remember from our operations slide, that changeover pressure selection dictates the setting of those first stage pressure regulators. So when you have a line regulator on the outlet, you don't want to set your changeover pressure very close to the line pressure that you want out of your panel. As a general rule of thumb, you want to target greater than a 2-to-1 pressure drop across your regulators. And thinking back to our flow curves, the reason is that if you maximize your pressure difference across the regulator, you can help maximize your flow performance. Now, this is a bit of a trade-off. Whatever changeover pressure you select will be the pressure that's left in the cylinder when the system considers it to be depleted. And so it can be desirable to maximize your cylinder usage by dropping the changeover pressure to as low as you can. But if you understand that there are regulators downstream that this panel is feeding, um, that lower changeover pressure comes at the expense of lower flow capacity through that downstream or line regulator. So to increase that flow capacity, you may choose to increase your changeover pressure. It's all a balancing act. So let's consider a very simple gas distribution system, and we'll talk about how the phenomena that we've discussed up to this point will apply. So in this case, we have two cylinders, and they're both filtered because we like to protect our regulators. And these are going to feed into a changeover panel. We've selected a changeover panel because we've decided that we want uninterrupted gas supply to our point of use. This changeover panel has a line regulator. You can see it kind of in the middle of the flow circuit in the dotted box there on the left. The SCO then feeds to a transport line. So this transport line goes to some other location, could be 100 meters away even, to the point of use. Because of that distance, we've selected a separate regulator panel. So we're using a Swagelok SPU in this case. And this is going to be located at the point of use so that the operator can dial in the pressure that they need quite handily without having to travel to where the changeover panel is at. So in this particular case, our cylinders are going to start off at 3600 psi. And we know that we need 25 psi at our point of use. So in order to help maintain decent flow, we're going to select, say, 100 psi for our transport line. And so our SCO might be selected with a line regulator with an outlet of 100 psi. And then in order to help balance gas usage and maintain good flow through the line regulator, our SCO has been selected with a 250 psi changeover. Now this system will work and have some very tightly controlled pressures in both the transport line and the point of use because of the multiple stages of regulation that are being used. However, if our point of use does have a significant flow demand, we may not be able to maintain that 25 psi across its flow range. So what would we be able to do about that? Well, if you look carefully, we've actually got 3 stages of pressure regulation between the cylinder and the point of use. And so if we get rid of the line regulator on our SCO panel, this is what that would change to. So without changing the changeover pressure, now our transport line, you can see has a higher pressure. That higher pressure in the transport line is going to allow more flow capacity through our SPU panel. So now our point of use may be able to achieve the full flow demand that it may want. What are the consequences of this? Well, the transport line now is subject to an increased supply pressure effect because there's only one stage of pressure regulation between the cylinder and it. And it will also see some additional pressure variation from the changeover action. Remember, our changeover regulators have to have a different pressure from one side to the other. So in this example, accounting for SPE and for the changeover action, we would expect the transport line to vary between 250 and 350 psi. But because that transport line is feeding a separate SPU regulation panel, we have our second stage of regulation there. The outlet pressure at the point of use is only going to vary between 25 and 26 psi. So we still have very good control of the pressure at our point of use, but with increased flow capacity. So once again, to recap, we've taken the system, we've changed from 3 regulators to 2 in series. We've retained good pressure control at the point of use, and we've improved our flow performance. Not to mention, we've decreased the cost slightly by removing one of the regulators. So when would we want to have an SCO with a line regulator? Well, here we take a very similar example, but in this case, the point of use is very closely located to the changeover panel. So we don't need to have a separate SPU or a point of use regulator. So in this case, we remove that panel and we take that regulation stage and we essentially apply it right at the SCO. So we have the same 3600 psi cylinder source, the same 250 psi changeover, and this time we set our line regulator to 25 psi on the outlet. Our transport line will vary by that same 26 to 25 psi that we saw on the outlet of the SPU in the previous panel. So our point of use is still happy. Okay, so just to review, when we're dealing with our gas distribution systems, we need to consider the effects of our regulators, right? We need to think about supply pressure effect, and we need to think about the lockup region and making sure that we're setting them with some amount of flow. And we need to consider the droop that we would experience as the flow changes in our system. We also need to be mindful of the number of regulators that we have in series because those will affect the flow performance. We need to think about the settings of our relief valves because those can be influenced by supply pressure effect. We don't want them opening prematurely and wasting our gas. And we need to be careful about how we how we select our changeover panels. So if you want to learn more, there should be an email coming up very soon with a link where you can request more information about your gas distribution systems. Um, if you do submit that form, you'll be reached out to by your local Swagelock Sales and Service Center. You can read more about it also on swagelock.com. We do have some literature on there for you to review. And you can definitely keep up with us by following us on our usual social media channels.
So thanks, Joe. I really appreciate it. Great information on gas distribution panels today. So we're going to take a few questions from the audience right now. We've already had a couple come in. Again, if you have a question, please feel free to hit the question button in the upper right-hand side of your screen and put it in, and we'll kind of go through those right now. So the first question, Joe, that we have is, do I need to turn the handle on my changeover assembly when I change the cylinder?
Greg, that's a great question. So if we think back to the Swagelock changeover slide, when we were looking at the 3 different panels there, each of them had a handle with an arrow on it. I think that's what you might be referring to.
Mm-hmm.
That arrow is there to allow you to select which of the 2 sources is primary. However, you do not have to operate that handle in order for the changeover action to occur. Once you've selected the primary source, you walk away and it will automatically, when that primary source reaches the changeover pressure, it'll automatically start drawing from the secondary source. You do not have to intervene.
Okay, that's great. Thank you. Second question we have here says, what would happen if I chose a changeover pressure that's lower than my outlet pressure? So what would happen if I chose a changeover pressure lower than my outlet pressure?
Another good question. We do see this from time to time. Usually it's when people are trying to, again, maximize their gas cylinder usage. They're trying to lower their changeover pressure as much as possible. Pressure regulators are only able to lower pressure. Uh, so if you were to select a changeover pressure that's lower than your outlet pressure, you would not be able to get your full outlet pressure out of your panel. Um, Similarly, if you were to choose a changeover pressure that is the same as the outlet pressure and you have a line regulator, you will have a serious impact to your flow performance. So again, you try to maintain that 2-to-1 pressure drop, or even better if you can.
Okay, that's great. And again, as a reminder, we have another question here too. But as a reminder, if you have other questions, feel free to put them in the question section in the upper right-hand side. We're getting several comments, Joe, about they've learned a great deal about SPE today. So loved the presentation. Uh,
Outstanding. Glad to hear it.
yeah, one more question. How will I know if my changeover is using the secondary source?
Ooh, yeah. Wow, lots of good questions. Um, so if you have a standard changeover panel and you're looking at the two inlet gauges, um, typically the changeover pressure will be listed on the nameplate of the panel. And so when you look at the inlet gauges and one of those gauges is at the changeover pressure that's on the nameplate, that means it has depleted the primary source and it is switched over to the secondary. Um, we have had a lot of requests for custom panels that might use, say, pressure switches or alarms to let them know remotely when this has occurred. So we do, you may not see them in the catalog, but we have made panels like that before as customs. So we encourage you to reach out to your local Swagelock sales and service center if you have those sorts of needs.
I got one last question that's come in. And the question is does the type of gas that you're using, does that matter? Does that have an effect? Or there certain gases that should not be hooked up to an automatic changeover, or can any type of gas media be hooked up to that?
Ooh, lots of great questions. So an automatic changeover should work for just about any type of gas. When you change a type of gas, you will change the flow characteristics. So if you think back to the flow curves that we were looking at, those were all for a particular species of gas. I think in our catalogs it's nitrogen. So if you have something with a different specific gravity, you may have more or less flow capacity as it flows through those regulators. And Swagelock does have a technical bulletin. I don't remember the number off the top of my head, but if you go to swagelock.com, you should be able to find the technical bulletin that shows you how to account for different gases uh, in your uh, in your systems. Another thing you may want to consider is materials of construction. So if you've got a gas like say hydrogen that's highly permeable, you're going to want to be cognizant of the sealing materials that you have. You don't want to have excess permeation. You can have some buildup, especially if it's located in an enclosed space. That can cause some problems for you. You also need to consider material compatibility. Make sure that the soft goods are not going to deteriorate when exposed to things like corrosive gases.
Great, thank you. Let's see. One other question just popped in. Do you mean the two-stage regulator system is the best solution for most gas distribution systems? So basically the question, Joe, is are two-stage regulator systems generally speaking the best solution for a gas distribution system?
Unfortunately, I cannot say what is the best solution for most gas distribution systems because a lot of them are very unique. What I will say is, in the examples that we showed, those were based on some examples that we had worked with customers on in the past. And very often, optimizing the number of regulators in line is a great way to help maximize the performance. But uh, I, I would not necessarily go out and say, you need to have this number of stages in order to have it operate best. Certain processes are going to be more sensitive to supply pressure effect and pressure variations than others. So when you need to have really tight pressure control, you may want to consider 2 or more stages of regulation for sure.
Okay, great. Well, that seems to wrap up the questions that we have. I'm putting an announcement on the screen now, or in the announcement section now for everyone. If they're interested in learning more about Swagelok and our gas distribution systems, there's a link in the announcements that will take you to a page on our website that will help you to learn more information about that. We're also going to trigger a quick poll for everyone in attendance that just helps us understand how well you guys enjoy the presentation today, and make sure that that we understand and make sure that you got the information out of the poll, out of this webinar that you were interested in. So please feel free to answer that question there. And then with that, we thank you for listening to Swagelok's presentation on gas distribution systems. We greatly appreciate it. And again, please feel free to reach out to your local Swagelok Sales and Service Center for more information, and have a great day.